Have you ever wondered how a GPS figures out every possible route to your destination, or how a game AI can explore all its potential moves? Well, today we're diving into the logic behind exactly that, how to find every single path through a complex branching structure. So, let's frame the problem. Imagine you're at the entrance of a huge maze with a bunch of different exits. How would you systematically find and map out every single route from where you are to every single one of those exits? That's the core question we're tackling. But our map, well, it's going to be a digital one. And that map is a data structure called a binary tree. Now, this is a really fundamental concept in computer science, so learning how to navigate it is an absolutely key skill. So, what even is a binary tree? You know, the easiest way to think about it is like a family tree, but with one really strict rule. Every parent, which we call a node, can have two kids max, a left child and a right child. And the whole thing starts from one single ancestor at the top, the root. Okay, so in our maze, what are the finish lines? In a tree, we call them leaf nodes. A leaf is just a node at the very end of a branch. It's one that has no children of its own. Every single path we're looking for is going to start at the root and end at one of these leaf nodes. Let's make this real with our specific example. We're given a tree that looks like this. 1, 2, 3, null, 5. So what does that mean? Well, 1 is our root. It has 2 children. 2 and 3. Then node 2 has a null left child, meaning nothing's there, and a right child, 5. Our mission is to find every single path from the root to a leaf. The answer we should get is 1, 2, 5, and 1, 3. So how do we actually pull this off without getting lost? We're going to use a super powerful algorithm called depth-first search, or DFS for short. And honestly, the name gives you a massive clue about how it works. The best way to get DFS is to go back to our maze. Imagine you pick a hallway and you just go. You go as deep as you possibly can down that one corridor. When you hit a dead end, that's our leaf node, boom, you've found a path. You jot it down, then, and this is the magic part, you retrace your steps. You backtrack to the last intersection you were at and you try the other direction. You just keep doing that until every single path has been explored. All right, enough theory. Let's actually watch this strategy in action. We're going to walk through our example tree step by step, exactly like the algorithm would. Okay, first things first. We begin at the very top, the root, which is node 1. The first thing we do is add it to our current path. So far, so good. Remember, this strategy is depth first. We want to go deep. The convention is to always try going left first if we can. So we move from 1 down to its left child, node 2, and we add that to our path. Our journey so far is 1, 2. Now we're at node 2. We try to go left, but there's nothing there. It's a dead end. So we try going right, and there we find node 5. We add it to our path, which is now 1, 2, 5. And would you look at that? Node 5 has no children. It's a leaf node. That means we found our very first complete path. We take that path, format it nicely, and store it in our final list of answers, 1/2/5. Awesome. Okay, now for the most important step in this whole thing. We've hit a dead end, so we can't go any deeper. We have to backtrack. We essentially hit the undo button on our last move. We pop the 5 off our path, which takes us right back to where we were before, at node 2. So, we're back at node 2. Have we explored all our options from here? Well, we tried left. That was empty. And we just came back from the right. So, yeah, we're totally done with node 2. Time to backtrack again. We remove 2 from our path, which takes us all the way back to the last major intersection, the root, node 1. All right, we're back at the start, node 1. We've now fully explored everything on the left side. So what's next? You guessed it, we go right. We travel down to node 3 and add it to our current path. And bam, just like that, we see that node 3 has no children. It's another leaf. So we record our second path, 1, 3. Now from the root, we've explored the entire left side and the entire right side. Our search is officially complete, and we've successfully found every single path. So seeing it visually makes a ton of sense, right? But how does this elegant idea actually translate into code? You might be surprised by how simple and direct it is. Check this out. Every single action we just took has a direct counterpart in the code. Adding a node to our path, that's just t.append. Checking if we're at a finish line, that's a simple if statement. Exploring deeper, that's where the function calls itself. That's recursion. And that magic undo button, backtracking, it all comes down to one beautiful little line. t.pop. That one command removes the last node and takes us one step back on our journey. So as you can see, the code is surprisingly clean. But if we had to boil this entire process down to just one essential concept, what would it be? It's all about backtracking. Seriously, this is the secret sauce. Backtracking is what makes this whole exploration smart. It's a methodical way of remembering the choices you've made, and when you hit a dead end, it lets you perfectly undo your last choice and try something else. It is a fundamental pattern for solving tons of problems that involve exploration. So if you take away just one thing from all this, let it be this simple mantra for this kind of search. Explore deep. When you find what you're looking for, record your success. Then, and this is key, retrace your steps to find what else is out there. And that's really how you do it. That's how you find every path in a binary tree. It's just a powerful combination of going deep and backtracking. So the question I'll leave you with is